To this point, we already considered a wide range of quantum systems, describing particles moving in 1 or 3 dimensions, and also considering the case of spin. And when we look at these examples from the perspective of the 4 postulates, we see that they provide a comprehensive and unified description of all these varied settings. But in one particular way, we kept our life quite simple, and this is because we obtained our wave functions or quantum states from solving the stationary Schrödinger equation only. However, according to our 3rd postulate, the time dependence of the quantum state is really a bit more involved, as it arises from the time-dependent Schrödinger equation, where the state and the Hamiltonian can both depend on time. We only obtained the stationary variant of this equation from what are 2 interlinked assumptions, namely, firstly, that the Hamiltonian is indeed independent of time, and secondly, that we can then separate out the time dependence of the quantum state and write it in a very particular form. This then allowed us to reference all properties of the system to one particular time. I simply denote this time-independent part of the state by dropping the time argument, so that's just the state at time t equals to 0. As we have emphasized before, what we ended up with takes the form of the eigenvalue equation for the Hamiltonian. And this means, for instance, that the energy of the state is precisely known. We can verify this by working out the energy uncertainty. Here, the first and second moment just gives us the eigenenergy and its square, and the uncertainty hence vanishes indeed. And what is perhaps even more concerning, when we work out the probabilities and expectation values in these states, then they do not depend on time. Recall that an overall factor in front of a state does not have any observable properties at all. But energy is just another observable of this system, and hence should come along with a probability, while properties in the world around us certainly change. Therefore, we should ask if these features are really general and look a little bit closer at our assumptions. We will do this in 2 steps. In the present chapter, we still assume that the Hamiltonian does not depend on time, and then construct the most general solutions of the time-dependent Schrödinger equation from the solutions of the stationary variant of this equation. This we will simply achieve by applying the superposition principle to states of different energy, and this suffices to describe the dynamics of systems for which the energy overall is conserved. We will also introduce the concept of the time evolution operator to write this general solution in a very compact form. In the next chapter, we will consider the case that the Hamiltonian itself depends on time as well. We will see that the system then can indeed change its energy. We will approach this by methods that utilize the time evolution operator generalized to this case. Often enough, we can then still take a stationary system as a reference point, and this will result in the concept of transitions, which we will then approach by adopting a perturbative approach. So much what we will do in the present chapter will also serve as a preparation for the next one. Okay, so let us turn to the dynamics of stationary quantum systems, hence systems with a time-independent Hamiltonian. Our plan for this chapter is the following. We will start out by general considerations, which contain 2 key elements. First, we describe the general solutions of the time-dependent Schrödinger equation from the perspective of the superposition principle. Secondly, we introduce a very powerful general way to think about these solutions, which is based on this so-called time evolution operator. This will be followed by 3 examples, where we study the dynamics of a free particle, the harmonic oscillator, and the spin. Perhaps surprisingly, as we progress through these examples, we will see that the resulting dynamics actually becomes increasingly more simple. To prepare our discussion, let us first retrace our steps that led to the stationary Schrödinger equation. Recall that at the time when we first did this, we did not have the Dirac notation. So we start from the time-dependent Schrödinger equation, which we now write in this Dirac notation. And then we inserted this specific trial solution where we separated out the energy dependence in what is essentially the Planck rule, involving an energy En, which is just a constant. When we take the temporal derivative, this energy appears in front of the wave function, while the time dependence of both sides is indeed identical. The stationary Schrödinger equation then results by simply cancelling this common piece, where we exploit that this is just a complex number which can be pulled to the front. Now recall that when we solved the stationary Schrödinger equation, we often enough employed the superposition principle. We found some independent solutions and then combined them to fulfill our boundary and continuity conditions. And the interplay of these three mathematical features, the boundary and continuity conditions and the superposition principle, was particularly apparent when the problem took the form of a differential equation, which we of course could sidestep in some cases by using algebraic methods. When we now proceed to the most general time-dependent solutions, we will just exploit the same concepts, only applied to the original, more general time-dependent equation. Well, this is certainly now always a differential equation, to the very least in terms of time. And because it is first order in time, any solution is completely fixed by specifying the quantum state at a certain time, say t0, which we can view as our initial condition. This gives even more force to our first postulate, where we say that the quantum state determines all properties of the quantum system. So this then also includes its time evolution. And it is also still a linear equation. The quantum state appears linearly in every term on both sides. This means that when we have found a particular time-dependent solution, we can multiply this by a constant, and this will still give us a solution. That's because such a constant can again be pulled to the front and then be cancelled. So we can use this, for instance, to normalize the state at some time, and then perhaps wonder whether it remains normalized at all times. More on this in a little while. But beyond this, we can also add any two solutions, and the result is still a valid solution. This we can see again by inserting the new candidate solution into the original equation, and then we can pull the terms apart. And when at the end we combine these terms again, we see that everything works out fine. So these are some very general consequences of the linearity of this time-dependent Schrödinger equation. And what we see here is that the superposition principle also applies to the solutions of this time-dependent equation. But as a consequence, we can now add all possible solutions of states with different energy. When we deal with bound states, this is just an ordinary sum. And when we have extended states, this will be an integral, where I denote the stationary solutions just by the energy and keep a separate index L to account for any possible additional degeneracy. And in the most general case, we can have both. So we end up with a state that involves stationary states with different energies. And because these energies enter the time dependence, this can in general no longer be written as a product of a time-dependent part and a time-independent part. In essence, we can now have time-dependent properties, but the details depend on the coefficients that appear here. These coefficients are really quite general. For instance, we can give them different values even for states of the same energy, hence degenerate states. However, the boundary and continuity conditions also apply to this equation, and in particular we want the state to be normalizable at all times. Fortunately, for any given situation, we can work this out once and for all. This follows when we exploit that the Hamiltonian is Hermitian, and so the solutions of the stationary Schrödinger equation are orthogonal to each other. Just for completeness, let me mention that for the extended states, we would formulate this using the Dirac delta function. With this, the normalization condition just involves the absolute squares of these coefficients. And in this condition, the time dependence drops out. Each time dependent factor simply absolute squares to 1. So when we normalize the state at one point of time, it will remain normalized at all times. Next, we will return to the observation that with the state given at a certain time, our initial condition, the solution at all times overall is also fixed. In this approach here, this means that with the initial state given, we can determine all the coefficients and hence turn the general solution into a very specific one. Well, for this we again exploit the orthogonality of the solutions of the stationary Schrödinger equation and assume that they are also normalized. So we use that we can turn these states into a complete orthonormal basis. Hence, the coefficients can be obtained by taking the scalar product of such a basis state with the initial state. We then say that we have expanded the state in the basis of the stationary states and call the coefficients expansion coefficients. The completeness of this basis is also the reason why this construction covers all possible physical solutions of the system. Finally, with all of this in place, we can give these expansion coefficients a direct physical meaning. Namely, according to the measurement postulate, they give us the probability to find the associated energy in a measurement. This is because quite generally these probabilities just involve the squared expansion coefficients of the observable in question, and here we now apply this to the energy observable, hence the Hamiltonian. So energy remains quantized when we look at the bound states, while in the range of the extended states we find a continuous range of energies, and there these expressions are interpreted as a probability density. With this we can, for instance, give general expressions for the average energy, hence the expectation value of the Hamiltonian, as well as for the corresponding second moment, and now in general the latter differs from the square of the former one. So now we have states for which the energy uncertainty can be finite. However, for the given case of a stationary system, we find that these expectation values are still time independent, and so are the energy probabilities. When we later study systems with time-dependent Hamiltonians, we will see that this is a consequence of energy conservation, which still persists in this modified form for the stationary systems that we study right now. However, when we look at our examples, we will soon see that even for these, real dynamics becomes visible when we turn to other quantities. But before we get to this, let us look at another solution method based on the so-called time evolution operator, which clarifies some of the general features that we've encountered so far. In the second method, we further focus on the aforementioned feature that the initial condition at some time t0 determines the solution at all times. Well, t0 here is arbitrary, so there should be a general relation between the states of a given solution at any two times. And because the Schrödinger equation is linear, this should again be a linear relation. So this really defines an operator, which we call the time evolution operator. This is a very abstract definition, but we can make it very concrete, and indeed in two related ways. First of all, we can use the power of the Dirac notation to rewrite our earlier solution obtained from the superposition principle in a very compact way. For clarity of notation, I developed this here by focusing on the bound states with discrete energies, but the sums just become replaced by integrals when we include the extended states into this description. So we write our general solution, including our explicit form of the expansion coefficients, exploiting that the energy eigenbasis is orthogonal and can be properly normalized. And then we simply pull the scalar products in these expansion coefficients apart, thereby isolating our initial state. And that's already it, because everything in front of this is just the time evolution operator. There we see that for our stationary system, it actually only depends on the time difference, which is a natural feature given that there is no explicit time dependence in this problem. So this is something that we could indeed have anticipated. There are indeed some other very general features, but these are easier to grasp when we first recast this expression into a second, even more compact form. Let me first write this down. It is this expression here, just a single exponential of the form that we have seen already before in the time dependence, but with the energy replaced by the Hamiltonian. This beautiful expression can be verified in a very instructive way. Well, first off, let me clarify what it means to have an operator in the exponent. As any function of an operator, this is defined by the corresponding power series, so by this expansion here. But do not worry, we do not need to come back to the series all the time. We will just use this when it is absolutely needed, because many properties of these expressions are very general. For instance, time appears in this expansion just as in a normal power series, and from this we can derive that the derivative of u with respect to time is a very simple expression, really just as if we applied the chain rule directly to this exponential function. But this can be put into a form that resembles the Schrödinger equation. And indeed, when we exploit this relation for our new general expression of the solution, then we see that this indeed fulfills the Schrödinger equation too. So this is one very general way to verify this very compact form of the time evolution operator. A bit more mundanely, when we apply this time evolution operator to any stationary state, the Hamiltonian just becomes replaced by the corresponding energy. And the resulting expression is the same that we get from our more explicit expression in terms of these stationary states, where we again utilize their orthogonality and normalization. You can easily check this yourself. As these states form a complete basis, both expressions then define the same operator. So this is another way to verify this compact expression for the time evolution operator, and indeed directly related to the more explicit one. There are two more important features. First of all, when we set both times equal, we should get the identity operator. And this is indeed true for both expressions. When our compact form, this can be seen very directly, while in the explicit form, this becomes the resolution of the identity, so the standard expression of this operator in an orthonormal basis. Secondly, when we turn the role of the two times around, we should obtain the inverse of the operator. But by looking at our expressions, we can get the same effect by taking the Hermitian conjugate of this operator. This works out because the Hamiltonian is Hermitian, and so the only effect is the complex conjugation of the I in front of the time difference, but this has the same effect as interchanging these times. And now mathematically, this means that U is a unitary operator. This is an extremely useful property when we look at the effect on the scalar product. Let's do this quite generally right away with two possibly different time-dependent solutions psi and phi, so two solutions that can have different initial conditions. We first express these in terms of the time evolution operator, That's the same operator in both cases, as it applies to all initial conditions, and then transferred from one argument to the other using the definition of the Hermitian conjugate operator. And now using the unitarity, this is just the inverse operator, and by definition the remaining product of the operators just becomes the identity. So this drops out, and we see that the time evolution from the Schrödinger equation preserves all scalar products. This includes the scalar product of a solution with itself, showing us once more in very general terms that the normalization remains intact over all times. But it also means, for instance, that two states that are orthogonal to each other at one point of time will remain so for all times. So these are some very general insights which we can exploit to drastically simplify many of our considerations. Let me therefore summarize the key features of this time evolution operator for stationary systems. It generates the time evolution of the quantum state for any initial condition. It can be compactly written in terms of the Hamiltonian, or explicitly in terms of the solutions of the stationary Schrödinger equation, showing us also that it only depends on the difference of the times. We can also determine this operator by solving a Schrödinger-like equation, with the initial condition being that it is the identity operator at equal times. And it is a unitary operator, which is really useful for calculations involving the scalar product. In some cases, it is indeed easiest to solve the Schrödinger equation generally by using this operator. But in many others, an explicit solution can only be obtained for suitable initial conditions, if at all. So to see how this all may work in practice, let us turn to some examples.